Okay, great. Yeah, thank you all for coming here so early in the morning. So to wrap this up, in this last set of lectures, what I want to do is explain to you, with the help of a concrete example, how we'll now think about phase structure in the many-body out of equilibrium setting. And then in the last hour, we'll put everything that we've learned together in the last like 2 days and talk about the discrete time crystal phase. Okay? So what we learned yesterday is that in a many-body localized system, it really doesn't make sense to think of an equilibrium ensemble average such as the Gibbs average. Okay? Your system is never reaching that equilibrium state. It's violating ergodicity. So usually when we're thinking of phases of matter, you're evaluating order parameters in this equilibrium state. But now that's just not sensible anymore. Okay? Moreover, we want to be thinking about systems at very, very high energy densities, highly excited states. So you want to ask now, how do we actually define phases of matter in some crisp way outside of this equilibrium framework? Okay? So we need a new way of thinking about phases of matter. And actually this is, it's really nice because it gives us a completely new paradigm. Okay? And this paradigm of how we think about phases of matter, when you're in thermal equilibrium, so when you have a thermalizing system, this agrees with what you would expect from a Gibbs ensemble, but it also works out of equilibrium. Okay, so it's like a generalization. So the way this works, it goes under the name of localization protected quantum order or eigenstate order. Okay, so the basic idea is that, as we were discussing last time, usually in a thermalizing system, highly excited eigenstates have volume law entanglement entropy. They're very entangled states. Okay, but in a many-body localized system, even a highly excited eigenstate, one that corresponds to infinite temperature, actually only has area law entanglement. Okay? And usually you associate area law entanglement with ground states of gapped quantum systems. Okay? So you want to think of area law entanglement as preserving quantum coherence in some sense. And if you were to go in and you were to measure ground state properties in some usual thermalizing gap quantum systems, they can show you long-range order, they can show you various nice features, okay? But what's nice is that MBL somehow promotes very, very highly excited eigenstates to have properties similar to ground states of gapped Hamiltonians, okay? So this means that we can now go in and in individual, very, very highly excited eigenstates, we can go in and measure correlation functions and order parameters like you would do in gapped ground states, okay? And these can now show patterns of order in individual states, okay? And now notice, last time we were talking about the eigenstate thermalization hypothesis, and the ETH tells you that properties, local properties, order parameters evaluated in individual many-body eigenstates agree with those of a Gibbs ensemble at the right temperature, right? So this framework of looking at patterns of order in individual states, when your system is thermalizing, it agrees with the usual definition that we all know and love, or the usual frameworks for thinking about phases. But in the out of equilibrium setting, it gives you something new. Okay? And what we'll find is that this kind of framework allows us to have order in settings that would be, or types of order that may be forbidden in equilibrium. Okay? So in equilibrium, we have various theorems which tell you what kinds of order are possible at what temperatures and what spatial dimensions. For example, Peierls Mermin-Wagner theorems is one example of this class of results. And this out of equilibrium setting will allow us to get around some of these results. Okay? The last thing I'll mention before going into before discussing an explicit example is that even though we're going to be talking about order parameters evaluated in individual highly excited many-body eigenstates, this is very useful because it gives us a formal way to define order. It'll give us a formal way to talk about singular changes that happen as you go across phase transitions. But you may say that this is practically of very little use, okay? Because if you're an experimentalist, you can't really prepare an excited, individual, highly excited eigenstate in the middle of some many-body spectrum, okay? These are very finely spaced. So this is supposed to be the many-body spectrum. These are very finely spaced. The level spacing between these is exponentially small in system size. So as an experimentalist, you simply do not have access. You may be able to prepare the ground state, but you simply do not have access to an individual, highly excited many-body eigenstate, okay? But despite that, even though we're going to use these eigenstates to formally define order, what we'll see is that these notions of eigenstate order translate into measurable dynamical signatures that you can actually see in a lab setting. Okay, so it's not just a formal device. The formal device is very helpful, but it also translates into measurable consequences. Okay, so the upshot is that we've gone from a notion of equilibrium phases of matter to dynamical eigenstate phases. Okay. And what this means is that not only do we now have a dynamical distinction between thermalizing phases and many-body localized phases, but as you tune some parameter, I'm going to leave that unspecified for now, you can actually tune transitions between different varieties of MBL phases. Okay, so in thermal equilibrium, in phases that do thermalize, you have all sorts of thermalizing phases, right? You can have symmetry broken phases, you can have paramagnets, you can have topologically ordered phases. So you should ask, in systems that don't thermalize, which are MBL systems, can I still have different kinds of MBL phases? And the answer is yes. Okay, so that's really cool. And not only is the answer yes, but you also get new varieties of phases that would not be allowed otherwise. Okay, so that's the localization protected quantum order. The localization gives you a way to get orders that may be forbidden. So let's look at this in the context of a concrete example, because I think everything will be much clearer then. So I'm going to consider system that we've discussed before, which is the transverse field Ising model. Okay, so let me start with uniform transverse field Ising model. Okay, and I can rewrite this in Majorana language and in fermion language. So let me do that because we'll use it later. Okay, so okay. So these are three equivalent formulations of the transverse field Ising model. Okay, so this is the model written in terms of spin degrees of freedom. Okay, so this is already written in a many-body language. So these are just Pauli matrices on every site. You can do a Jordan-Wigner transformation, and the transverse field Ising model is a system of free fermions. So these are my Dirac fermion operators. When you do this transformation, this looks like, this is actually a superconducting chain. It's a Kitaev model, right? And it's superconducting because you have these pairing terms, C dagger, and CC, okay? So you take the transverse field Ising model, it's mappable to this system of fermions. Naively, if you look at this model, this may look like it's not, it may look like it's not a system, a simple binding model like you might be used to, which just involves particles that are hopping, because it also has this two-particle creation operator. But this is standard. This is standard from BCS. You can now take this and define these Majorana fermion operators. Okay, so this is what we had discussed last time, or a couple of lectures ago. These Majorana fermion operators are real. They can be written in terms of the Dirac fermions. Okay, so these basically look like minus I C dagger J minus Cj, and these look like Cj dagger plus Cj, okay? So these can be written as superpositions of creation and annihilation operators in the original fermion language. These are real. They satisfy A dagger 2j is A2j, and they have the right commutation relations, okay? So right now this is just algebra. It's all well known. And you know that the original transverse Ising model has Z2 Ising symmetry. Okay, the Z2 Ising symmetry in spin language is the product over all I, xi. When I use these capital letters, I really mean sigma zi. Okay, it's just a shorthand. So this is the same as sigma ix. Okay. So the transverse Ising model has this Ising flip symmetry. Okay, and what this does is this is the product on all sides of the sigma x operator. So if you're working in the sigma z basis, your spins are either pointing up or down, you have some magnetization on every side. This corresponds to coming in and flipping all the spins in the z basis. Okay, so that's your Z2 symmetry. The same Z2 symmetry exists in the fermionic language as well. Okay, so in the fermionic language, this basically is a product over 1 minus C dagger I Ci on all sides. Okay, so in the fermionic language, what this is counting is whether you have an even or odd number of particles. Okay, because of these creation operators that come in pairs, C dagger, and Cc, particle number as a whole is not conserved, but it's conserved modulo 2. You can only create or destroy particles in pairs. So whether or not you have even or odd Ising symmetry in the fermionic language maps to whether or not you have an even or odd number of particles. Okay, good. So now, what do we know about the phase diagram of the 1D transverse Ising model? Okay, so if this is J over H, okay, or let's write it as J minus H, that's 0, okay, and that axis is temperature, okay. So what we know is that for G greater than H, the ground state, which is 0 temperature, is a ferromagnet, while for J less than H and at any finite temperature, okay, so this whole region here, this is all a paramagnet. Okay, and this just follows from, so why is this a ferromagnet? Okay, so let's look at it when H is 0. Okay, so let's look at the model when J is either much bigger than H or H is 0. Then you just have the Ising interaction term, the sigma z. You know that you have two degenerate ground states when H is 0. That looks like all spins either pointing up, that's the up state, or all spins pointing down. Right? So these are your two ferromagnetic states that are related by the action of the symmetry. So these have symmetry breaking, right? These break the Z2 symmetry, because when you act with this Ising operator on this state, you get this state back. Okay? Whereas everywhere else, the state, like deep in this paramagnet phase, just looks like spins pointing along the x-axis. Okay? At any finite temperature, we know from the Peierls theorem that there is no Z2 symmetry breaking in one dimension. Okay? And the reason that happens is that at any finite temperature, you have a finite density of domain walls. Okay? The domain walls are completely delocalized. So if you go in and you measure an order parameter like a spin-spin correlation function, you have all these fluctuating domain walls, and as a result of that, you just end up getting something that looks that's 0. Okay, so there is no long-range order at any finite temperature in one dimension. Okay, in equilibrium. Okay, good. So, you know, these two states are the symmetry broken states. Okay, these are the two minima that are related by the action of the symmetry. But actually what we want are the symmetric eigenstates, okay? We know that the model has the Z2 symmetry. So all your eigenstates can be chosen to be eigenstates of that Z2 symmetry. So the symmetric eigenstates, when H is 0, they look like these plus or minus Schrodinger cat states. Right? Which corresponds to taking in either an even or an odd superposition of these two minima, or of these two degenerate minima, right? So this is the case when h is 0, and now as you increase a little bit of h and you go along in this direction, what you'll find is that, you know, these up and down operators, this is a gapped model, these will get dressed a little bit, but more or less your eigenstates continue to look like some versions of these states, okay? And in the infinite size limit, the splitting between these guys, e plus minus e minus, is exponentially small in system size, because to go from one state to another, you have to create a domain wall, you have to sweep it across the entire system, and that's a very, very high order process that happens at order L, okay? So this is an exponentially small splitting between these two degenerate ground states, which goes to 0 in the infinite size limit. And when it goes to 0, you can choose one of the other of these symmetry broken states. But in any finite size system, these are your eigenstates, okay? So this should all be reviews. Anything that I'm saying not clear? Okay, good. So now the ferromagnet is characterized by the presence of long-range order. So you can go in and you can measure a connected correlation function like Zi, Zj minus, okay, and we'll look at very large separations, and this is not equal to 0 in the ferromagnet in the ground state, okay, so that's in the ground state. But at any finite temperature, as we were saying, you have these fluctuating domain walls. So if you go in and you measure a correlation function like that, you get 0. And likewise in the paramagnetic phase, where your eigenstates look like they point along the x direction for the ground state, but at any finite temperature, they just look like these disordered paramagnetic states. Again, a correlation function of this kind is 0. Okay. So fine. So this was all as we expect. Okay. But now this whole picture changes very dramatically when you have disorder in your problem, okay? So I can come in and I can take these couplings here and I can make them disordered. And by that I mean that these vary from site to site. Okay? And when that happens, this is a problem. This is a disordered transverse realizing model, which maps to a disordered superconducting chain or a disordered chain of Majorana fermions. But yesterday we learned that Anderson proved in 1958 that if you have a system of non-interacting electrons with disorder in the couplings, then all your excitations all your single particle excitations are exponentially localized. Okay, so for this single particle problem, we know from Anderson that all your eigenstates are localized. How you go from the fermion language to the spin language, I'll come to in a few minutes. But the main point is that the excitations in the spin language look like domain walls. Okay, so if your eigenstates are either all up or all down, the excitation is, you have some domain wall between your eigenstates. Okay, so when H was 0, okay, and Ji is J, so there's no disorder. Okay, so this comes back to a question that was asked yesterday about, when H is 0, you just have a diagonal model in the Z's, so all your eigenstates are very simple, right? So you have a ground state which is doubly degenerate. These look like the all up and the all down. But now what you can do is you have a whole manifold of states where, say, you have a pair of domain walls, okay? So you have exactly one domain wall. So let's say you have that, and then you have something flipped in the middle, and here you have its reversed partner. Okay, so this is the one domain wall state. And then you can have two domain walls, n domain walls, okay? So as you keep going up, you basically have more and more possibilities for where you stick those n domain walls in. Okay, there's exponentially many, this is order n domain walls. There's exponentially many states here, and they're all going to be degenerate, okay? So you have this highly degenerate manifold where the only thing that labels what your energy is how many different domain walls you have. And now, as soon as you turn on a small amount of H, all these degenerate manifolds can just immediately mix under the action of the H, because what the H does is it flips a spin, which corresponds to a hopping of the domain walls, okay? So these domain walls then hop, and all of these degenerate states look like delocalized states with order n domain walls, all fluctuating like crazy, okay? However, instead of starting with ji equals j, if I started with a genuinely disordered problem, okay, then what you would get is all of these different states that we wrote down would not be degenerate with each other. Instead, you would have a whole spectrum of states, all of which are unique, have some different energies, which just correspond to different patterns of up and down spins, right? And their Ising reversed partners being exactly degenerate with it when H was 0. Right? So now you just pick any pattern of Ising spins. It's not degenerate with any other pattern because of the disorder in the problem, but it's degenerate with under the action of this Z2 symmetry, which flips everyone. Okay. So now again, if you want to build symmetric, if you want to build states that have a definite eigenvalue under the Ising symmetry, what you do is take even and odd superpositions of each of these different states. Okay. So your entire many-body spectrum looks paired. Okay, so you have all of these different states here, and all of these different states here, and these states are exactly degenerate with these states, and these are your p equals 1 states, and these are your p equals minus 1 states. Okay, and now when you turn on a small amount of epsilon, once again, so this was a state which has some number of domain walls in different places, okay? But these domain walls are now getting pinned by the disorder. They can't just freely move around, okay? So these domain walls, which are like your single particle excitations, they remain stuck. So even when you turn on a small amount of epsilon, what you'll find is that your states basically look like these random patterns of up and down spins, dressed a little bit with these stuck domain walls, but the pattern with the plus cat state now is exponentially close in energy to this minus cat state. It's not exactly degenerate, but it's very close. Okay, so there's this pairing in the energy spectrum. Okay, but something very remarkable has already happened. Okay, so what's happened now is that you can take any state that lives at a very, very high energy density, and if you go in and you measure some correlation function, right, a connected correlation function, which is trying to probe long-range order as we did before, then this is not going to be 0, because what's happening is that your states here now look like some random pattern of spins, but they're all frozen. Okay, so this is you take a ferromagnet, and the ferromagnet, gets promoted to a spin glass. Okay. Because what happens now is when you measure this correlation function, you basically get either +1 or -1. It has nothing to do with those states. It's just some random sign. So let's just call it, I'm going to measure this correlation function, this connected correlation function in the ith eigenstate. And you'll get some sign of that eigenstate times 1. Okay? So, and this is just, the sign is just probing that when you're looking at your two spins, are you going to go across an even or an odd number of domain walls in measuring that order, okay? So, every single eigenstate now shows long-range order, okay? It's a frozen, glassy long-range order, but nevertheless, there's long-range order in every single eigenstate, even the ones that are extremely highly excited, okay? If you, because of this random sign, okay, so this is not inconsistent with the Peierls theorem, because what happens is that if you go in and you measure this correlation function, but you choose to average over all eigenstates, as you would do in a Gibbs ensemble, then you're averaging over this correlation function with a bunch of plus signs and minus signs, and the average as a whole will again give you something that's 0 or exponentially small, but every individual eigenstate can nevertheless show you frozen order. Okay? Yeah.
So the averaging is more coarse-grained in this sense. Like, it is measured over this sort of stacked domain walls, not
yes.
a grand scale, right?
That's right.
Okay, so you are like having an intermediate time scale, you have to build up another scale, it's a spatial scale, sorry.
That's right. So that's right. So the spatial scale that you build up is set by the localization length of your domain walls. You know, when h is 0, then everything is just exactly stuck. So this is exactly plus or minus 1. But when you turn on a small amount of h, things are not exactly stuck, but they have some, you know, exponential decays, and that gives you this spatial scale. But if you choose to average over things in energy space, then you just get something that's 0, an exponent, right? Okay. So good. So now what happens is that this old phase diagram that we had, it's now gotten replaced with a new one. And here, instead of temperature, you know, temperature is a concept that only makes sense in thermal equilibrium. Instead of temperature, we're going to write energy density. Okay. And what happens is that this whole, at every energy density now, instead of having no long range order, so you have a phase with spin glass order, okay? So this is long range ordered, and basically your ferromagnet has gone to a glassy phase, okay? So this is J minus H again. And in this free fermion problem, you can exactly solve everything, and you know that the transition actually happens exactly along this line. So everywhere here is spin glass. Every state looks like, every eigenstate looks like a state like that. And over here, you have a paramagnet. But now your paramagnet is also localized, okay, by the disorder. So your ground state could be some pattern of spins in the x basis pointing that way, and then every excited state just has some localized flipped spins, okay? But everywhere here you have long range order, and everywhere here you don't. Okay? So intuitively what happened is that what these theorems like Peierls, Mermin, Wagner theorems, what they're trying to capture for you is the interplay between energy and entropy in different dimensions, okay? So the lack of long-range order at finite temperature in one dimension is the statement that in one dimension at any finite temperature, entropy always wins, okay? And you destroy your long-range order. That was the statement about you have domain walls, they're fluctuating, they destroy the order. But here, as a result of localization, you prevent the entropy from winning, okay? Entropy is a statement about ergodically being able to explore all of these different states. But because these domain walls or these excitations get pinned by the disorder, your entropy is being killed effectively, and so you end up with long-range order even at finite energy densities. Okay, so this illustrates localization protected quantum order because you really need the localization to be able to see this. Yeah. If in both cases you have what?
Like frozen.
Yes. Yeah.
You said that we have long range order because there we have frozen configuration of domain. Also, it kind of related. And in parameters, why don't we have?
Okay. So usually when you're talking about long range order, you're talking about long range order of your order parameter. Your order parameter here is sigma z because it's measuring the magnetization on some one site. And this is the case where the connected is actually important, okay? So there's a difference between connected correlation functions, which is genuinely probing the correlation between something that's not just coming from each individual site having some expectation value. So that's where the cat states become important, okay? Because you're absolutely right that if all I had was some product state like this, and then I go in and I measure Zi in this product state, I'll get say +1. If I measure Zj, I make it and then if I measure Zi, Zj, that will be equal to Zi times Zj, right? And that's minus 1. But then if I look at this connected correlation function, it's 0. But notice this is not true for a cat state, okay? Because for the cat state, these guys are 0, but Zi, Zj can still be minus 1, okay? So the fact that in this phase, your eigenstates, so we'll come back to cat states over and over again over the next hour. So that's actually really, really important that at any finite size, you're going to pick the eigenstates of your system to respect the symmetry of your problem. The symmetry here is the Ising-Flip symmetry, okay? And because of that Ising-Flip symmetry, on this entire side of the phase diagram, your eigenstates actually look like these plus or minus Schrodinger cat states with global long-range order, okay? Yeah?
So in a sense, the cat states are necessary to build this intermediate scale range, right? So based on your argument, because we have a 0, like you cannot really pinpoint the small scale that you would be able to before if you had not cat states.
So by what exactly do you mean? By intermediate scale, you just mean the localization length?
Yeah, localization. So
yes.
Is the localization preconditioned on the existence of cat states?
No, no. So the order is preconditioned on the existence of cat states.
The order,
yes. So this is localized and that is localized. Both phases are localized, but one is a localized paramagnet with no long-range order, and the other is a localized spin glass, which is a generalization of a ferromagnet, which does have long-range order. Okay. So the order depends on the cat states, not that. Okay. So, yes, I'm not going to go into details on all these free fermion mappings. Okay, but the picture you should have in mind is that when you have this Hamiltonian written in terms of your Majorana degrees of freedom, the way it works is that on every site, you can go in, okay, so this is each site J, and you go in and you associate Majorana, 2 Majorana fermions with each site J, right? So that's this statement. Usually you had C daggers or C's, fermionic creation or annihilation operators on every site J, but now you've taken a C dagger J and a CJ, and you've associated with every site this Majorana operator of A2J and Majorana operator of A2J plus 1. Okay? So this is the Majorana, which is A2J minus 1. This is A2J. This is A2J plus 1, A2J plus 2, and so on. Okay? And in this way, the way these terms work is that your J's basically couple between different cells, okay? And your H's couple Majoranas on the same supersite. And what you're going to do is you have this Hamiltonian written in terms of your Majoranas. You can easily diagonalize it. So your H is basically written as some I times AJK. This is a matrix. This is antisymmetric. And this has eigenvalues which are basically plus or minus I epsilon k. So that's the, so this in the Majorana language, the system has particle hole symmetry. All your single particle eigenstates, so right now I'm talking about single particle eigenstates. All your single particle eigenstates come in pairs, which is epsilon and minus epsilon. Okay, so you build this up, that's 0. And then if you want to build your many body states, okay, so when I'm talking in spin language, I'm implicitly already thinking about many body states because there's 2 to the L spin configurations, okay, that's exponentially many. Here, I'm always thinking about free fermions, you know, this is going from 1 to L, okay, J and K. So here you're thinking about single particle wave functions, and the way you go from your single particle fermionic wave functions to the many body states is you basically come in and you occupy different single particle wave functions, okay? So in this language, a given many body eigenstate corresponds to basically you you take this, you diagonalize it, you end up with some eigen creation operators with some energies, and then you basically have some product over K occupied of B dagger K, which acts on the vacuum. Okay? Yeah.
Could you describe how the matrix AJK looks like a block form also?
Yeah. So it's basically exactly this, right? Because these are your Majoranas, and so your A basically you're coupling. So the zeros on the diagonal, and then you have J's and H's basically, right?
And anti-symmetry. What is the anti-symmetry?
There's probably going to be minus signs. Yeah. Right, because these fermionic operators are, if you switch the order of them, you pick up a minus sign. So the way you write the matrix, you'll just find it like that, okay? And then you diagonalize this matrix. You get the eigenvectors in terms of these Majorana modes. And then you can take those, and just like you can go from these Dirac fermions to Majorana operators by taking superpositions, you can go from the Majorana eigenmodes to creation operators of these Dirac types by taking those superpositions. Okay, so these are basically superpositions of Majorana eigenmodes. And in the original fermionic language, they have like C's and C daggers in them. Okay, which is because your eigenstates are not eigenstates of definite number. Okay, but at the end of the day, what you've done is you've taken this doubled spectrum, and you've rewritten your Hamiltonian in terms of epsilon k, some B twiddle dagger k bk. Okay, that is your Hamiltonian. Yeah. Okay, so then you're just going to build your many body states by filling these guys, right? And so now this particle hole symmetry gives you this redundancy. Okay, so I know I'm going through a lot, but this is all well-known stuff, so you can look it up. So this model here, so here J goes from 1 to L. This J goes from 1 to L. But by the time you've gone to the Majorana language, you've doubled your space, right? You've associated 2 fermions with every single Dirac fermion. So that doubling is encoded in the redundancy of this spectrum, because with every state here, there's another state there. So you only have to keep track of, you take the epsilon of epsilon plus and epsilon minus, which are just negatives of each other, and you conjugate them to make one Dirac fermion with that energy. Okay, so the ground state corresponds to filling all these negative energy states, and then you build your higher excited many body eigenstates by making particle hole excitations where you destroy something here and create something there. Okay, so your 2 to the n, this object, right, which is your Hamiltonian. This is running from some index k goes from 1 to L, and your 2 to the L many body eigenstates in this fermionic language are just built by occupying different numbers of these k modes. Okay, so this degeneracy that I was mentioning earlier between the even parity and odd parity in the spin language, okay, in the fermionic language it comes from the existence of a Majorana zero mode. Okay, so you can see that these eigenvalues are coming in pairs plus or minus epsilon k. So 0 is very special. Okay, 0 is its own partner. Okay, so when your spectrum has a Majorana zero mode, you can either occupy that mode or not occupy that mode, and you get exactly the same energy. Okay, so in this fermionic language, the degeneracy is between many body states where that Majorana mode is occupied versus not. And those are, of course, degeneracies between states which have an even number of fermions or an odd number of fermions, because you're going in and you're either acting with this zero mode or not, right? So you can already see that if these are your J's and those are your H's, okay, when H is exactly equal to 0, there's this Majorana that lives on this end of the chain, which has nothing acting on it, okay? So it's already, this Majorana mode is an eigenstate of your problem with 0 energy when H is 0, okay? And likewise for this guy, okay? So in the ferromagnet, when J is much, much bigger than H, you have these Majorana zero modes, and the even and odd pairing of your Ising spectrum corresponds to the occupation or not occupation of these of some Dirac fermion formed from these edge Majorana modes, okay? And because these two edge Majorana modes are spatially separated by the length of the system, instead of having something strictly at zero, you actually get something that's exponentially split. This is a exponentially split zero mode, because basically when you turn on a small amount of H, this mode will now couple to that guy, but with a very small coupling having to do with the entire, going across the entire system, okay? So good. And now when we go to the flow case setting, I'm going to use the same kind of picture, yeah.
You said this mode will come to the very end, like in the length scale of the whole system. Could you give an intuition for this? Like,
yeah.
How come that the zero mode has its property? Like, what happens in the time? Like, how do I understand this a bit more frequently?
So I think the way you should think about it is when H is zero, okay, you have a decoupled mode here. This you can just see pictorially, and a decoupled mode there, okay? So your eigenstates are just this guy alone and that guy alone. Now, when you turn on a small amount of H, this alone is not an eigenstate, okay? It's not an eigenstate because it's coupled via this H to this guy, right? And then, so if you take this matrix that I had with 8J, 8J, 8J like that, and you try to find an eigenvector for it, which is 0, okay, with eigenvalue 0, which is a zero mode, what you'll find is that this eigenvector roughly looks like 1 H over J, these on different sites, okay, H over J squared, H over J cubed, and so on. Because what's happening is that this is now no longer an exact eigenstate, but if you start trying to do perturbation theory, it's going to mix with different things at orders which go as H over J. So for it to actually mix with something way over there is H over J over to the L, which is the exponentially small in L coupling between those modes, okay? And that gives you this exponentially small in L splitting. Yeah, so your different modes, basically this mode is exponentially localized on this end of the chain, and that mode is exponentially localized on that end of the chain with a small h, and the splitting between those is exponentially small in system size.
I'd like to get an overlap between eigenvectors then, I mean, what is happening in the calculation? Like, can you sketch the calculation to get this exponential?
I mean, I just did, so,
okay.
Yeah. So I'm saying that if you just, all you're doing is, so let me make sure I get the matrix correctly. Okay, so your G, sorry, so all those guys are right, so it's alternating between. Okay, so that's this antisymmetric matrix, and you want to find an eigenvector for it which has eigenvalue 0. So when H is 0, you can see that I can just stick in 1, 0, 0, 0, 0. These correspond to the different spatial sites, and if you stick that in, when H is 0, you get exactly 0. Okay. Now, when H is not 0,
you have this H over J. Okay.
Exactly. So then to get the eigenvector which is giving you 0, okay, what you'll end up doing is basically you'll have 1, 0, h over j, 0, h over j squared, 0. Okay? Does that make sense? Because if you plug that in, you have to keep canceling it. So this ends up being an eigenvector of this system. So if this goes forever, then this is a 0 eigenvector. And now you can see that it has weight, which starts off here, and then it keeps decaying exponentially. That's the calculation. Okay. Good. So, all right. So the last bit that I'll say before the break is, actually I'll make 2 or 3 comments.
Yep. Each side, right? What we want here is for every side.
No, so this is your matrix. This is a 2L dimensional matrix. And you want to get 2L different eigenvalues out of it. And what I'm saying is that your 2L eigenvalues come in pairs, which is epsilon and minus epsilon. Okay, so there's L such pairs. And one of the pairs is 0 and minus 0, or more precisely, e to the minus L and minus e to the minus L. And if you want to construct the eigenvectors that belong to these eigenvalues, those in real space look like this.
Okay.
Because this is in real space, right?
Okay, and the eigenvectors in real space.
Exactly.
Okay,
yeah. Because this is the Majorana that lives on site 1, 2, 3, 4. Yeah. Okay, so a few comments are, what's an order parameter for this transition that takes you from the spin glass to the paramagnet? Okay, so you can formally, using the eigenstate structure, define a spin glass order parameter. Okay, and what this looks like is, what I was telling you earlier is, we don't, so if I go in and I measure Zi, Zj in some given eigenstate n, okay, I actually want to be, if I only do an average over different Zi, Zj's in a given eigenstate, I'll get plus 1s and minus 1s, and this will go to 0. So I really want to be averaging this object squared, okay? So that gives me spin glass order parameter that is non-zero in every single eigenstate n, okay? So the transition is between this object being order 1 in the spin glass phase and between being 0 in the paramagnet. Okay, so this is a generalization of the usual notion of long-range order that you would probe. But here again, I've used this kind of expectation value of some observable in an eigenstate squared. Okay, so now you can ask, okay, this is somewhat artificial, you're taking the expectation value in an eigenstate, squaring that, it's good for a diagnostic, but how do you actually measure it, okay? And it turns out that things that involve expectation values taken in eigenstate squared are intrinsically related to dynamical correlation functions in your system. Because if you do something like, if I want to measure an operator like that, okay, just in general, what I'll do is I can insert a complete set of states, and I can have here right? Because I just stuck in a set of states here. I have e to the IHTs, O of t in the Heisenberg pictures, e to the IHT, O, e to the minus IHT, okay?
Like a structure factor.
Exactly. That's right. But then what happens is that if I decide to wait very, very long, okay, then you're ending up in a generic spectrum, these differences in eigenvalues are going to be incommensurately spaced with respect to each other, okay? So if you wait very, very long, all of these different phase factors for energies that are not equal to each other will dephase, okay? And after that dephasing, what you'll end up with is sum over m such that em equals en, and generally this will be the diagonal ensemble, okay? So you'll end up with something like that squared, okay? So if you measure 2-time correlation functions and decide to wait very long, right, then you'll naturally end up with things which look like expectation values of operators in different eigenstate squared, okay? So this is just a way of telling you that even though this spin glass order parameter looks a bit artificial, actually the dynamical correlation functions, this is something that an experimentalist can measure, right? Okay, you say that, okay, maybe an experimentalist cannot measure this in n alone, that's fine. I can now average over n, and that's still okay, because I have that, okay? So that's okay, because this, even after you average over n, this quantity, the 2-point function averaged over eigenstates goes to 0 because of fluctuating signs, but the squared 2-point function averaged over eigenstates does not go to 0, okay? So even if an experimentalist can prepare a generic initial state, which actually looks like a superposition of all these different eigenstates and measures some 2-point correlation function in that, you can get, by probing these correlators, you can tell whether or not you have order or not, okay? So this is actual numerical data. For this model, I am measuring this 2-point correlation function, and in the spin glass phase at late times, this is approaching some non-zero constant, okay? But in the paramagnet and the thermal phase, because this is all at finite temperature, this is an average over finite temperature, this is going to 0, okay? So even though you cannot prepare these highly excited eigenstates, as an experimentalist, you can go in and prepare some initial state that's very easy for you to make, like some pattern of up spins, and then you can measure this 2-time correlation function, autocorrelation, this is what you measure all the time, and you'll find that in the spin glass phase you get something non-zero, whereas in these other disordered phases you get something, disordered here I mean just no long range order, paramagnetic phases it goes to 0, okay? And now you want to ask, okay, so, you know, by using this correlation function, you've distinguished between the spin glass and these two phases, but how do you tell the difference between the paramagnet and the thermalizing phase? Well, now instead of measuring a correlation in Z, measure a correlation in X, and in the paramagnet, your sigma X operators look like your L bits, right? So the L bits were these quantities that were conserved by the dynamics, and they look like the, you know, when J is 0, but your model just looks like HIXI, that's kind of where we started yesterday, right? So you're exactly at J equals 0, your L bits are the sigma X operators. Now when you perturb away a little bit, you'll end up dressing those, but the dressed operators still have large overlap with the bare sigma X's. So that's why if you now measure this correlation function, it'll remember some memory and go to some non-zero value, whereas these other correlators go to 0, okay? So by measuring this pair of physically observable correlations, you can distinguish between all 3 phases. Yeah?
If you look more carefully, then spin glass state does not really look like when it goes to 0, right? It's non-literal.
Yes, but this is a finite size simulation. When you do the finite size scaling, it will go to 0. And it's also what's happening is that this is an Ising even operator. So this Ising even operator has overlap with some. So you want to ask, what do the L bits look like in the 2 phases?
No,
I know. So yes, I'm answering it. So in the paramagnet, your L bits look like dressed versions of your X. But in the spin glass, your L bits, which have to respect the Ising symmetry, they actually look like domain wall operators, which are like Zi plus 1. Okay? So your L bits, you need n conserved quantities. They basically look like dressed versions of this. So, you know, your effective tau I is this, and there's n minus 1 of them, and then it's also this global parity operator. Those are the quantities that you have. So if I'm measuring a correlation function of X on some one site, by the time you do the dressing, has some overlap with this L bit, because both are Ising even. And so the small part of this is what you're measuring in this phase. Yeah.
Question, how would you write the eigenvectors of tau I, like in the old, like in the base of the set? Or like?
In the bare basis.
Yes.
Yeah. So these dressed, so this is the same thing what, you know, so when you're thinking about the equilibrium phase diagram of the transverse field Ising model, what Hastings showed, right, is that when you have a gap, right? So this is the notion of adiabatic continuity, if you will. When you have a gap, you can start with your eigenstates at some one value of parameters that you know. So for instance, the ground state. We know that when H is 0, the ground states look like your cat states in the sigma z basis. And now when you add a little bit of H, what Hastings showed is that, well, when you have this gap, then the ground states with a non-zero H is related by a local unitary transformation to the ground states without the H, okay? And that's that local unitary transformation that takes you from the physical bits to the L bits that we were discussing yesterday. So those are the ones that relate these eigenstates, right, in the undressed and dressed languages, okay? So for the MBL problem, what's really nice is that even though there's no actual gap, and even though we're not talking about ground states, there is still a notion of a mobility gap in some loose sense, so that there's still this local unitary transformation that takes you from all your unperturbed eigenstates when H is 0 to the actual eigenstates when H is non-zero. Okay, so it's just some local unitary transformations. You should just think of it as more or less your state looks like what it is in the sigma z language, but then you can pick up some corrections, which are some fluctuations coming from this local unitary transformation. So it'll look like some superposition, but the superposition has most of its weight near the original basis. And it's that local unitary transformation that takes you from the physical bits to the L bits, like we discussed yesterday.
Okay, so I'm going to say, like, if I were to write an eigenvector like what you wrote for V.
Yes, yes.
And for that, like, just to connect the
Yeah, yeah.
Could you please help me in the...
Yeah, so like I wrote for V, what you've done here is when H was 0, your eigenvector was just living explicitly on one side. When H is non-zero, it picks up this exponential tail. Okay, so this is the tail in real space. Now you have an exponential tail in Hilbert space, if you will. Okay, so what you have is, say you're doing the usual MBL problem that we were doing yesterday. Your L bits, when you only had Hi sigma Zi, your eigenstates were just product states in the Z basis. Okay, now I add in some J sigma dot sigma. So your eigenstates now look like some Uj, okay, some local unitary transformation acting on something like that. But if this is a local unitary transformation, what you'll get is some superposition where, you get basically this state, and then you'll go in and you'll make fluctuations about it. So say you flip one spin, but now these are fluctuations in Hilbert space. So say you flip one spin. So then your state more or less looks like this state, okay, but one spin gets flipped somewhere. And then another, you have the sum over all, one spin flips with some coefficients, okay. And then you have two flips with some coefficients. So the state gets completely dressed, but all the corrections about this come with coefficients that go down exponentially.
Okay, so that is now in Hilbert space.
Exactly. Yeah.
How does this disorder change the nature of the phase transition because the transcriptizing model usually has this one form of pizzeria?
Right. Yeah. So in the presence of disorder, the phase transition is what's known as an infinite randomness phase transition. So the properties of the infinite randomness phase transition with in the ground state were actually worked out by Daniel Fisher all the way in 1995. Okay. So there, the idea is that it's a new kind of universality where you're going from when you're trying to get this phase transition, right, you start with a disordered problem, and under some kind of effective RG, like what you do is you go in and in your problem you say that, okay, I have some J's and H's, let me take the strongest J, okay, and make that bond happy. So if that J was positive, let's make those two spins aligned. Okay, and then there's everything else. Then once you made these two spins aligned, you kind of integrate that bond out of it and generate some effective coupling between the sites surrounding that bond. Then you go back in and you look, okay, what's the next strongest coupling, either that's J or H. Now you make that happy, you integrate it out, and this is only a well-defined procedure if your original, you can think about, why should I make this j happy at the cost of everything else? Well, if that j was 1,000,000 times stronger than everything else in your problem, then it makes sense that you should make that happy, right? So this procedure is controlled by a flow in this RG sense towards infinite randomness. So what you'll find is that even though you started with some bare distribution of your couplings, as you keep doing this renormalization group, your couplings get broader and broader, so you really start getting some couplings that are much, much larger than others. It gets broad on a log scale, okay? So that's this flow towards infinite randomness that controls this transition. And so then you get this infinite randomness kind of phase transition between the spin glass and the paramagnet. And even though Daniel Fisher did this for the ground state, you can actually show that the math he did, instead of making some one bond happy, which is what you would do in the ground state, you can choose to make it unhappy just with a negative sign. And his math looks exactly unchanged, whether you want to get this state or the ground state or that state or the ground state. Okay, so this whole line is an infinite randomness critical line. And now you can ask what happens, all of this, I was doing this for the free problem. And of course, I want to now make everything interacting. So you can ask what happens once you add in interactions. And the fate of this spin glass to paramagnet phase transition in the presence of interactions is actually still unknown. And there's a lot of reasons to think that there's actually, this is unstable to the presence of interactions, a critical point. Okay? The critical point ends up becoming there's some intervening thermal phase, but deep over here you have an MBL spin glass, and deep over here you have an MBL paramagnet, okay? And because of this kind of infinite randomness RG procedure, what you can show is that even though all your single particle eigenstates here are exponentially localized and here are exponentially localized, actually at the critical point, they're only marginally localized. So they have instead of being exponential, they're stretched exponentially localized, and your entanglement, instead of being area law, is actually log law. So your entanglement looks like it's log L, which is similar to what gapless CFTs look like, right? So here it has some universal log L entanglement at that critical point. Yeah. Okay. All right. Sorry, I'll make one last comment. So I don't have time to go into this. The same kind of analysis that I did can be used even for thinking about topological order, okay, or symmetry protected topological order at finite energy density. So you can take a model like the toric code, okay, and just like you have constraints on what kind of symmetry breaking order you can get at finite temperatures, you also have constraints on what kind of topological order you can get at finite temperatures, okay, and usually, once again, this picture is that at finite temperatures, you have some finite density of topological defects, and those will destroy some topological order that you're trying to protect, okay? So when people are trying to do topological quantum computation, the big challenge for them is trying to actually cool the system way down to 0 temperature, okay? But what this analysis tells you is that if you have disordered systems, if you have a disordered version of the toric code model, the excitations that would fluctuate, and you have vortex excitations and you have charge excitations, those excitations which would destroy your order can now get pinned by the disorder and localized again. So you can once again get glassy versions of topological order. Okay, so whether this can be used to try to do some kind of topological quantum computation even at finite energy densities is an interesting idea that various people have thought about at various points. So all of this kind of generalizes to the interacting setting, it generalizes to topological order, it generalizes to SPT order. So that's kind of a summary of localization protected quantum order for you. Okay.